So have a look at page 3 of your worksheet. Okay. So page 3 of your worksheet should be June 15 P41. Okay. Now, this part in A, define specific latent heat. Now, specific latent heat is a definition from your notes. You can just say it's the heat energy per unit mass required to cause a phase change at constant temperature. Okay. So this one here is a general definition. They're not asking you whether it's from solid to liquid or whether it's from liquid to gas. They're just asking you what is specific latent heat. So the definition that you will put in is that you just say it causes phase change. You don't need to mention whether it's from solid to liquid or from liquid to gas. If they specifically mention latent heat of vaporization, that one would be for liquid to gas. But if they specifically ask you latent heat of fusion, that one would be for solid to liquid. So then you need to specifically mention what is the phase change involved. But in your case, you do not need to because this is a very general case that they've just mentioned. Okay. And also one other thing that I should probably mention here is this. Because specific latent heat is a physical quantity, make sure that your definition is all in terms of physical quantity only. Mean to say, like in your case, this is heat energy per unit mass. So make sure that your quantities are in terms of physical quantities. Because there have been cases where people write something like this, just to tell you what I mean. If you had written it as this, heat energy required to cause 1 kg of substance to change phase at constant temperature, this one would have been wrong because 1 kg here is actually unit. All right. The only thing that is wrong about this entire definition here is the fact that you use a unit here instead of definition. If you are being asked to define a physical quantity, like say specific latent heat, the definition must all be in terms of physical quantities only. So do not use any units. The moment they see that you use any units inside to describe a physical quantity, they will generally mark you as wrong. Okay. So this one here is an example of a wrong answer. I mean, when you read it, it seems okay, but it's actually not accepted. Okay. So you have to be careful in how you word your definitions sometimes. If it's in terms of physical quantity, it must be in terms of physical quantity. If it's in terms of units, then everything must be in terms of units. Okay. This one, you'll see more of this as you go along in the other chapters. Now, if you look at B, you have an electrical heater immersed in some melting ice that is contained inside a funnel as shown in this figure. The heater is switched on, and when the ice is melting at a constant rate, the mass M of ice melted in 5 minutes is noted together with the power P of the heater. The power P of the heater is then increased, and a real reading of mass M of ice melted in 5 minutes is recorded when the ice is melting at a constant rate. Okay, so notice a few terms here that they've mentioned that is something that you've encountered in the notes earlier. Specifically, they told you that they only collected the mass when the ice was melting at a constant rate. Okay, the one that I did for you just now was for boiling. This one is for melting. So same principle applies because you're trying to determine some sort of latent heat, which is usually Q over M. this M here must be the mass that has changed phase. Okay, you need to determine the mass that has changed phase here. Okay, you need to collect that mass that has changed phase. Usually you can only do it when you have constant boiling rate or when you have constant melting rate. Constant boiling rate is for when you're trying to find latent heat or vaporization. Constant melting rate is when you're trying to find the latent heat of fusion. In your case, you're trying to find the latent heat of fusion. So you need to wait until your substance is melting at constant rate. So this one here is constant melting rate. And notice that they also collected the mass that has changed phase in 5 minutes for a particular power setting. And then after that, they repeated it with a different power setting. They told you that the power of the heater is increased, and they now collect the mass that again has melted in the same time interval. They used 5 minutes before, they're also using 5 minutes now. Okay, so they're using the same time interval. All right, so then after that, they told you that data for power P and the mass M is shown in the table below. In part 1, they ask you to complete that table and find out the mass melted per second for each power of the heater that you've just used. So here, mass M melted per second. You already have the mass in 5 minutes here, and this is your power. If you want mass melted per second, you need to take your mass divided by your time taken. Your time taken is actually 5 minutes. You need to change to seconds. Okay, so if you use your calculator to calculate for the first row, at 70 watts, mass divided by time here would be 78 grams divided by 5 minutes change to second. You should get getting 0.26. And then after that, for 110 watts, mass divided by time will be 114 grams divided by 5 minutes change to second again. So you get 0.38 grams per second. So this is the mass M melted per second. Okay. All right, then the next part is where you will apply the method that we just learned from the notes. Now, use that data in your completed figure to determine a value for the specific latent heat or fusion L of the ice. Okay. So this one, when you want to write it out, just be careful a bit. Okay. You cannot possibly insulate out your entire apparatus so that you can make heat loss to be negligible. Your heat loss will be significant here. Okay, so I mentioned just now earlier that you can actually cancel them off provided you have same temperature difference and same exposure time. But there's also another thing for you to note here. In your current case, it is not heat loss to surroundings, but rather heat gain from surroundings. Let me just give you one thing that I mentioned earlier just now. I mentioned earlier just now in the lesson that heat energy always flows from higher temperature to lower temperature. Okay, so say for example, if I'm talking to you about boiling, if I'm trying to boil water now, I use an electrical immersion heater here. Okay, my water will eventually boil at 100 degrees Celsius, and my temperature of my surroundings is 25 degrees Celsius. So you can imagine that because this part here is at 100 degrees Celsius, this is at 25 degrees Celsius, heat will actually be flowing from 100 degrees Celsius to 25 degrees Celsius. This is actually going to be, in my case, heat loss to surroundings. Okay, such that if I wanted to write some sort of energy equation here, this one would be something like this now, where I will say that heat supplied by heater equals to heat to vaporize liquid plus heat loss to surroundings. Okay, this one would make sense for you here. Whatever heat that you've supplied from the heater, part of it went into vaporizing the liquid and part of it also went into the surroundings. Okay. Now, when it comes to melting, this is a bit different now. When it comes to melting, say you again have the same beaker here, and then now you fill it out with ice, a lot of ice, a whole lot of ice. And then after that, you try to melt it. Now your ice, when it melts, is at 0 degrees Celsius. But your temperature, your surroundings, let's just say your room temperature is 25 degrees Celsius. This one, you can see there's a difference in which part is higher temperature, which part is lower temperature here. Okay. The ice is actually lower temperature than your surroundings. Okay. And because heat always flows from higher temperature to lower temperature, what you would end up with is that you actually have heat gain from surroundings. Okay, here you actually have heat gain from surroundings. Okay, because here you can see is higher temperature. This one here is lower temperature. Whereas the one before this one was lower temperature, but this one is higher temperature. Okay, so the direction of heat flow is different here for your case. Whereas the first case is heat loss to surroundings, the second case is heat gain from surroundings. Now, when you want to write out your equation, it will actually be heat supplied by heater plus heat gain from surroundings plus heat gain from surroundings equals to heat to melt solid. Okay, so the equation is worded slightly differently here. Instead of saying that it is heat loss to surroundings, it's actually heat gain from surroundings. And it will be on the left side of your equation, not on the right side. Okay, so you will actually have to apply this one for this current case. Okay, so if I say heat supplied by heater plus heat gain from surrounding equals to heat to melt solid, this one, if I write it out in equation form, this one will actually be VIT plus H equals to ML. Now, if I divide this by time, this one will become VI plus H over T equals to M over TL. Okay, and the VI itself is actually my power. This one is what you are seeing right over here. I've actually changed it to in terms of per unit time rather than using this original equation itself. The reason why I use it as per unit time is because I'm given the value of the power and also I'm given the value of the mass per unit time. If you recall what you just did in the previous table, you found out the mass per unit time. So I'm just trying to change the equation to be in terms of per unit time. Okay, so if it is in terms of per unit time, this is what you're supposed to get. P1 plus H over T equals to M1 over T times L. Then you get P2 plus H over T equals to M2 over T times L. So you have two equations. Take equation 2 minus equation 1. These two are supposed to be the same because same exposure time as well as same temperature difference, so they cancel all. Eventually, you get P2 minus P1 equals to M2T minus M1T times L. So your power is 110 minus 70. Your mass per unit time is 0.3 minus 0.26. Multiply with your L. Eventually, your L will be 333 joules per gram. Just like that. Okay. Okay, then after that, if you want to move to the next part, the next part is asking you to find out the rate H or thermal energy gained by the ice from the surroundings. So see here, it's actually asking you about the heat gain from the surroundings. Okay, we know it must be heat gain from surroundings because the surrounding is having a higher temperature than the ice itself. Okay, and because they mention rate here already means per unit time. Okay, so if you want to find the rate of heat energy gain from surroundings, you can actually just use either equation 1 or 2 from above, because that equations actually have H over T. Okay, so in my case, I use equation 1. P1 plus H over T equals to M1 over T times L. I know the power is 70. H over T as well. I want to find the mass per unit time is 0.26. The L is something that I just found before this, is 333 joules per gram. Eventually, my H over T is going to be 16.7 watts. Okay. So you can also likewise repeat this for equation 2 if you wanted to. You will actually get back the same answer. Okay. So this one, when you look at this one, this is all the workings in terms of per unit time. You don't have to use it in terms of per unit time if you don't want to. You can actually have another different way of doing this, just that it's a bit more tedious. Now, if you did not want to use your equation in terms of per unit time, you want to use it like this equation form, VIT plus H plus ML, it's actually also possible without you changing it to per unit time. Okay. So if you wanted to do it that way, you will probably have to look at this part here. Okay. So if you don't want to write it all in terms of per unit time, where you just wanted to use this equation straight, this one you can actually just write it as, you see VIT is actually PT also, okay? You can actually just use this equation straight where you say is P1T plus H equals to M1L, and then P2T plus H equals to M2L. Your time, you actually already know. It's actually 5 minutes. So you know the power, you also know the time. It's actually 5 minutes. And then when it comes to the mass that you collected over 5 minutes, it's actually from the table in your previous page. The one that you have here is the mass collected in terms of 5 minutes. This is your M1, M2. Okay. So you sub all those values in after subtracting equation 1 from 2, you actually will get back the same value of L. Okay. There are no issues there. If you wanted to use it this way, it's also fine. If you find this one to be more comfortable for you, you can also use this method. And then after that, when you move on to the next part where you are trying to find the rate of heat energy gain from the surroundings, you can also still maintain the same working. You can either use again equation 1 or equation 2. This time you find out specifically your heat gain from surroundings. It's not yet per unit time. You will find out that your heat gain from surrounding is 4,974 joules, but you need to convert it to per unit time. All you just need to do is you just take that heat that you found, divide by 5 minutes. Again, you will be getting the same answer as the one that you have over here. Okay, so you can also do it this way if you had wanted to. All right, you don't necessarily have to just straight away change it to in terms of per unit time right off the bat. Okay. So hopefully this is clear. Okay, then if you're okay with that, let's move on to page 5. Okay, now page 5, June 15, P42. Okay, now define specific latent heat. This is something that we've just done before. It is the heat energy needed per unit mass to change the phase of a substance at constant temperature. Okay, so this one is a definition from your notes that you just need to reproduce. Now for B, this one is a beaker containing a liquid that is placed on a balance as shown. You have a heater of power 110 watts that is immersed inside the liquid. This heater is switched on, and when the liquid is boiling, the balance readings M are taken at corresponding times T. So now, a graph of variation of time T of the balance reading M is as shown in this figure below. All right. So this one is not really you trying to melt ice. Unlike the previous example, this is you trying to boil off water. Sorry, they didn't say it's water, they just say it's a liquid. This is you trying to boil off some sort of liquid. So what you can imagine is this. Your liquid is here. When your liquid starts to boil, the liquid will change to gas. So when your liquid changes to gas, the mass of liquid remaining, the mass of liquid remaining here will start to drop. And this is what you're actually trying to measure right now. Because you see, this beaker with your liquid is actually resting on your balance. What you're measuring here is actually the mass of the liquid that is actually remaining inside your beaker here. Okay. So when you try to plot a graph of mass versus time, you're going to get a decreasing value because you have more and more liquid being turned to gas. That's why your mass drops. Okay, so this is what you expect to see. Now, then after that, if you move on to the first part of the question, they want you to state a feature of the graph that tells you that the liquid is boiling at a steady rate. How do I know that you have reached constant boiling rate? Steady boiling rate here means constant boiling rate. Okay, so let me just write it here. If you're talking about boiling at a steady rate, this one is already referring to constant boiling rate. Okay, so how do I know that? So based on what I mentioned to you earlier, you just need to look at the graph that is straight. Okay, you look at specifically the gradient. All right, so I know that this has reached constant boiling rate or steady boiling rate because I noticed that the graph is straight, is having a constant gradient. Okay, so you can just say that because you see it's a straight line, because the gradient is constant. Okay, either one. If it's a straight line, it also means that your gradient is constant. Okay, so how would you kind of deduce it from here? You see, if I divide this into 2-minute time intervals, this is 2 minutes, this is 2 minutes, and then this is 2 minutes. This will be my corresponding mass changes. This is my delta M. This one will be my delta M. This one will also be my delta M. So you will notice that your delta M here, if you draw your lines properly, these delta M's here are actually the same. So this one here, you will eventually come to the conclusion that you have constant mass of liquid boiled off per unit time interval. Okay, this is constant mass of liquid boiled to gas per unit time interval. So therefore, is constant boiling rate. Okay, so it's only possible if your line was straight or if you have constant gradient in the first place. Okay, so that's one thing to note here. And then the next thing in your question is that they want you to use the graph to determine a value for the specific latent heat L of vaporization of the liquid. Okay, now, just now, when you look at the notes, we talk about determining the specific latent heat of vaporization. That one involves you trying to find the mass collected at two different power settings, right, for the same time interval. So only then could you find your specific latent heat of vaporization. So that time I told you that you cannot just simply ignore your heat loss to surroundings because it's quite significant. You have to do your experiment twice in order to find out the latent heat of vaporization. Now, for this particular question that you're looking at, you cannot do the same thing here simply because they did not give you any information about a second power setting being used to boil off the liquid. Okay, they didn't give you any information about a second power setting to boil off the liquid. So you cannot use the method that was just described inside your notes. So in your specific case here, you have no choice but to just ignore the heat loss specifically, all right? So here, if I try to write out the conservation of energy equation here for you, you actually have PT equals to ML plus heat loss to surroundings, okay? I don't need to use VIT here because I know that I already have the power. In the notes earlier, I wrote this as VIT, right? This is under the assumption I know the voltage and the current. But if I do not know that, I know the power is actually the same. Okay, VIT is the same as PT. Okay, so now if I ignore H, PT will now be equals to ML. All right, such that L will now be PT divided by M. Okay, so this M here, as I mentioned a number of times already, it should be the mass that has changed phase. In your case, it should be the mass that has changed from liquid to gas here. Okay, so to do this question, you want to use this equation. All right, you first need to ignore the heat loss first. You cannot use simultaneous equation here because you do have a different power setting here. Just ignore what I've just wrote here first. Okay, this one is actually an easier method to do. So if you wanted to find out the specific latent heat of vaporization here, you need to know the power, you need to know the time, and then you need to know the mass that has changed phase. Okay, now power, this one will be easy because you have it listed in your question here. Your power is 110 watts. Okay, now what about the time and your mass? Okay, so the time here, the time interval here, this one is determined by student. So make sure it is at least half the total time. Because you see, when you did your experiment, it's from 0 to 6 minutes, right? So what value of t do you want to use here? You should ideally make sure that is at least half the total time used. So say maybe, for example, right now, the t I want to use is 4 minutes. And this is my t now. So I want to then find out the corresponding mass that has changed phase. That one will be this one. This one will be my delta M. This one will be my delta M. Okay. So here my T being 4 minutes. My delta M here would be, if I'm not mistaken, this is 20 divided by 10. So each small square is actually 2. So this one is 372, if I'm not mistaken. Okay, now let me just write this. I could be wrong, but I'm trying my best here. So 372, this is 372, and then this one is in the middle of the box. This one is 342, 344, 345, if I'm not mistaken. Okay, so I could be wrong now because I'm just estimating from what I see here. So this one should be 372 minus 345, giving me an answer of 27 grams. Okay, so now I have the mass, I have the time, from which I can find out my specific latent heat. So L would be 110 times with a time of 4 minutes. I must remember to change it to seconds. Then divided by the mass change, this one is 27 grams, so it's 27 divided by 1000, change to kg. So 110 times 4 times 60 divided by 0.27, you should get the answer as 9.78 times 10 power 5 joules per kg. Okay, so the answer is actually quite close. The answer here is 9.83 times 10 power 5. If I round it up to 2 SF, this one is actually 9.8 times 10 power 5 joules per kg. This one I rounded up to 2 SF is also going to be 9.8 times 10 power 5 joules per kg. Okay, this one is one method that you can use to find your answer here. The one that the marking scheme use is a bit different, where they try to use gradient of the graph. So what they did here was this, because you see your graph that you had is actually a graph of mass versus time, giving you a line that looks like this, right? So what they did was that they're trying to use PT equals to ML also after ignoring heat loss, but they try to change it into a straight line equation, y equals to mx plus c, where the y-axis is your mass and your x-axis is your t, so that your gradient is actually P over L. Okay, so gradient here is equals to P over L. What you're supposed to do is to find the gradient, equate it to your power divided by L, so that you find out your L as this value. This is also another different way of doing it. Okay, so up to you which one you want. Okay, then last question here is state with a reason whether the value that you just determined in 2 is likely going to be an overestimate or an underestimate of the normally accepted value of the specific latent heat or vaporization of liquid. So if you ignore heat loss here to calculate out your latent heat of vaporization, is it going to be an overestimation or underestimation? So just now I explained to you, it's always going to be an overestimation. All right. If you ignore heat loss during your calculations, whatever you calculate will always be an overestimate because you're assuming more heat has been used here. Okay. So here, you know that you're going to be having an overestimate, but you need to explain first why. Because here you have heat loss to surroundings. You assume that heat loss is negligible, but there's actually heat loss to surroundings in practice. So the value here is going to be an overestimate. All right. This one, if you had wanted to write it, other than saying that heat is lost to surroundings, so the value is overestimate, you can probably also say this now. Heat loss was ignored during calculations. So the value is going to be an overestimate. Okay, this is one way of wording it also. You can just say heat loss was ignored during the calculations. So your value is going to be an overestimate. Okay, it's also going to be okay to use this. All right. So this one is for this question.